Carbonic acid is a relatively weak acid and therefore easily dissociates into bicarbonate and hydrogen ions. Bicarbonate can then further dissociate into hydrogen and carbonate ions. This dissociation process and reflective pH can be seen in the azimuth plot. As carbon dioxide dissolves into water, the amount of bicarbonate ions increases. This is because of the dissociation of carbonic acid into bicarbonate and hydrogen ions. Bicarbonate ions then reach a peak and start to decrease as it dissociates into carbonate ions, which are seen increasing. All the while, the pH is increasing and becoming more alkaline. The blue line shows where our oceans are currently sitting on this scale, and is labelled as expected change is a lowered pH. This is because there is decreasing dissociation into the final stage, this being the dissociation into carbonate ions. Dissociation is determined by a bicarbonate buffering system. Buffers are any chemical that can help maintain a pH range and therefore accommodate for shifts in hydrogen ion concentrations and resulting pH. The pH of any given substance is determined by its proton availability. When there is an increase in hydrogen ions, which have a positive charge, an increase in proton availability, and therefore a lower pH. The pH of oceans is naturally maintained by seawater, as seawater acts as a natural buffer. Seawater, like any good buffer, contains a weak acid, carbonic acid, and a conjugate base, carbonate ions. The process of keeping seawater pH maintained is with the use of carbonate ions to increase the pH, which has been decreased by hydrogen ions. As seen in the azimuth plot from before, the higher the concentration of conjugate base, the higher the pH, and therefore more alkaline the system. Although this is an effective and natural way of maintaining the ocean's pH, if the demand for carbonate ions gets too high because of an increase of hydrogen ions, this can impact negatively on marine life, which also rely on carbonate ions to survive. Going back to the azimuth plot, where the carbonate ions get used in the buffering system, there is less carbonate ions, therefore the expected change is a decrease in pH. The amounts of carbon dioxide present in the atmosphere and oceans can be seen in this graph. The resulting pH of the oceans is also shown. As you can see, the atmospheric carbon dioxide has increased by 74 parts per million at a rather constant rate since 1960. The trend of an approximate 25 ppmv increase every 20 years is also mirrored in the dissolved carbon dioxide in the ocean. As for the pH, as expected, it has been decreasing. The rate of decrease in pH is approximately 0.02 every 20 years. The rapid rate of increase of CO2 and decrease of pH has only been seen in the past 60 or so years. This becomes obvious when we look at this carbon dioxide concentration graph. In the past, the carbon dioxide levels have been maintained pretty well, but since 2008 and earlier on, the level of carbon dioxide has risen dramatically. Therefore, it has only been within the past decade that we have realized how much of a detriment carbon dioxide really is. There are two different future estimation scenarios when it comes to the concentration of carbon dioxide. The first and better case scenario for the concentration of carbon dioxide at the end of the century is 550 ppmv. The worst case scenario, which is the higher emissions scenario, results in a carbon dioxide concentration of around 900 ppmv. Either scenario, the carbon dioxide concentration will increase. Relating this back to temperature, as there is an increase in temperature, there is a decrease in pH. This can be seen specifically when we look at the pH fluctuations over a year in Bermuda, which is one of the most vast temperature-changing locations for ocean acidification data collection. The temperature in Bermuda is lowest during December through to March, and as expected, the pH is highest at this time. From April through to November, the temperature starts increasing, and this is when we start to see a decrease in the pH. Statistically, January and February have the lower sea temperature, and this is mirrored in the highest pH. On the other hand, July through to September has the highest temperatures, and in the graph, as shown, has the lowest pH. This reinforces reinforces the fact that the higher the temperature, the lower the pH because of greater amounts of carbonic acid. With a rapidly increasing carbon dioxide concentration and a rapidly increasing temperature, we will notice massive detriments to not only sea life but the whole world. The negative implications from the increasing acidity are detrimental to ocean organisms, especially those that use calcium carbonate as the building blocks of their shells. pH is important to keep maintained. Most chemical reactions that are essential for all living organisms rely on consistent environmental factors. When talking about ocean-found organisms, pH plays a big part. With a dramatic change of pH, most organisms would struggle to survive and die out before they could evolve to tolerate the new pH. Their chemical communication, reproduction, and growth would be directly affected if a change in pH was to occur. Most aquatic organisms prefer pHs of around 6.5 to 9. Even keeping within this pH range, slight effects in pH can have massive implications on ocean life. A slight change in the pH of water can increase the solubility of many heavy metals, phosphorus, and other nutrients. With an increase of nutrients, some species thrive while others die out. When the pH of water falls below 5 or rises above 9.6, the harmful effects become noticeable. The solubility of calcium carbonate is reduced outside of this range. This inhibits shell growth in most organisms. As stated before, carbonate ions are used in the buffering system to maintain the pH. When creating their shells, organisms take up carbonate ions that react with calcium to form the skeletal structure of their shell. When there is a lack of carbonate ions, shell growth is decreased. During this biomineralization process, if there is a lack of carbonate ions, there can be an oversaturation of calcium ions. This is when calcification happens. Calcification is the hardening of organic tissue by a deposit of calcium salts. This has massive negative implications and directly affects coral reefs. They go from looking like this to this, and eventually go to this. The integrity of their skeletal structures gets so weak that eventually it just flakes off into nothing. Coral reefs are so important for all sea life organisms. Not only do they keep them safe and provide a home for many organisms, they also keep us safe by protecting coasts from strong currents and waves. Furthermore, pH levels below 5 generally affect the reproduction of most fish, and because of this, many species will leave the area. Most organisms begin to die when the pH falls below 4. Basically, with a dramatic change in pH, most organisms will die out, and this will directly affect the food chain, and indirectly cause many other species who rely on those primary species to also die out. The change of pH will also affect many seafood industries, as our supply of seafood decreases. More than 1 billion people worldwide rely on food from ocean as their primary source of protein, and many jobs and economies around the world depend on the fish and shellfish in our oceans. This becomes a real issue. As you can see in this graph, there are 2 lines. The black line is representing where we are today. The red line is representing the worst case scenario, and the blue line is representing where we can go from here on to make it better. As you can see, the best case blue scenario is that we keep a relatively maintained pH. The worst case scenario and the path that we're on at the moment is the red path. The red shows a rapidly decreasing pH, and by the end of the century, the pH will drop around 7.7. With a rapidly increasing global temperature, and the amount of carbon dioxide being stored in the oceans increasing, the pH is decreasing. Things are not looking good for our world. The good news is it's not too late to turn things around now. The acidification of the ocean can be decreased using one of 2 methods. The current responses to ocean acidification are decreasing greenhouse gas emissions or leaving things just how they are. Scientists believe that the increasing acidity and increasing temperature are just normal environmental fluctuations, and this era will pass without any major detriment. This is where the doing nothing response comes into play. Although this might be true, the current trend is an increase in ocean acidification due to an abnormally high carbon dioxide concentration that has never been seen before in history.
It's harder to ignore this issue and do nothing, and therefore this is where making a change counts.
The second response is obviously decreasing greenhouse gas emissions. As stated earlier in the video, carbon dioxide is the offset of the combustion of fossil fuels. By reducing this offset, we're preventing the issue from acidification by stopping it at its roots. Although the heating of the planet may not be directly from atmospheric CO2 and could just be from the fluctuation in temperature as seen in the past, we can still minimize the acidification of our oceans by decreasing the amount of carbon dioxide that is present in the atmosphere to dissolve. So even if you don't believe in the controversial issue of global warming, our oceans will do better with a decrease of carbon dioxide emissions. We can reduce our carbon footprint by looking at less polluting energy sources to power our world, such as solar. Using solar power is an effective and more environmentally friendly, as there is no carbon emissions after construction of solar panels. As individuals, we can also help to reduce the carbon footprint by walking, riding a bike, or taking a bus to reduce the amount of pollution from vehicles. We can also do other little things to conserve energy, like replace incandescent bulbs with compact fluorescent lights, which use 25% less energy, and reduce our use of hot water. All of these things will reduce our carbon footprint, which will indirectly reduce ocean acidification. So in summary, ocean acidification is a real issue in our world today. The process of acidification starts with carbon dioxide dissolving in seawater and reacting to result in carbonic acid. Carbonic acid then dissociates further into bicarbonate and hydrogen ions, and then further to carbon ions. Carbonate ions are essential for ocean organisms, but are getting used in maintaining the pH of oceans. Organisms are affected by a reduced carbonate ion supply and reduced pH. The issue of ocean acidification can be solved simply by reducing our carbon imprint.